Hello and welcome to Product Rule. Basically, we're going to dive a little bit deeper into what some of the rules are and some of the shortcuts that are going to help us avoid that limit as h approaches 0. Okay, so our first example is looking at this ugly guy. This is a little bit tricky of a problem, and you want to be careful you don't go too fast. If you go too fast, then it's not going to really end all that well. The big catch here is the 16. If the 16 was not there, or if it were simply 16t cubed, I could say 3 times 16 is 48, t squared. Perfect. But because the 16 is there, technically I got to worry about this 3 and the 16 first. So it's kind of like 16 to the third, t to the third. Once I make that move, then I can just figure out what 16 to the third is, multiply it by 3, and then say that t squared. And I've got my answer. It's a little bit of a sneaky rule I just wanted you to see. Alright, so then this guy. This guy, be careful, don't just say it's 1 times 2x and the answer is 2x. Technically what we should be doing in this problem is foiling. So x times x squared is x cubed, x times 3 is 3x, plus x squared plus 3. Once it's expanded, I could then go to g prime of x. The derivative of x cubed is going to be 3x squared. The derivative of x squared is going to be 2x. The derivative of 3x is 3. And then the derivative of 3 is 0. And I like them in descending order better. So you 100% can solve this problem by just doing a little bit of foiling to be able to knock the problem down a little bit. An alternative would be to listen to this guy. Now this is Leibniz. He's one of the two inventors of calculus. What he basically discovered was, rather than having to FOIL that out, there are some instances where you cannot FOIL it out. So we needed some kind of a rule when two things are being multiplied. That rule became the product rule. The product rule says if you have two things u and v that are being multiplied, and you take the derivative, it's u untouched times the derivative of v, plus v untouched times the derivative of u. This is the more formal way to write it, but I kind of like the primes better. I just find it a little bit easier to multiply. Note, when he first published this, he got it wrong. He just said it's u prime times v prime, and then like in the second draft of the book, he fixed it. So occasionally that happens to us, and as we go deeper into the course, you're going to be more likely to make that mistake. But the official rule is if two things are being multiplied, you then have to apply the product rule. This is one of those rules where you're probably going to want to know its name. Alright, coming back to the original problem. One way to organize yourself with the product rule is actually to state what u is and what v is. Sometimes you're going to want to do this, sometimes you're in a hurry and you don't want to write this, but it's a nice option to have. List out what u prime is. The derivative of x plus 1 is 1. V prime is going to be 2x, just the derivative of this guy. So then I want to put it all together. My g prime is going to be u untouched times the derivative of v plus v untouched times the derivative of u. In case you're wondering to yourself, well, that's not the order he just said on the last page. The cool part is it doesn't really matter. So long as you have a prime matched up with a not prime, you get a lot of freedom with the product rule. Any way you want to put it together is okay, because at the end of the day, when we reduce it, we all have the same answer. And as a dyslexic such as myself, I like the fact that I don't have to stick to one rule. So it gives me a little bit of flexibility and more likely that I'm going to remember it. Alright, so if you really wanted to, you could let your 4/3 be u, and then let this x cubed plus 12x be your v, and then do a product rule on this problem. It's a little overkill, but I'm going to go this route just to let you know that the option does work. I got to imagine most of you would prefer to distribute and then go from there. Note that my u prime would be 0. And my v prime is 3x squared plus 12. So my product rule is going to be u times v prime plus u prime times v. Because it's 0 times, I'm not even going to really worry about what that is, and then I have my answer. 4x squared plus 16. So you do get a lot of options as to which route you want to go. So again, I got options. I could either FOIL this together, or I could product rule it. Both ways work just fine. It's just a matter of personal preference. I'm going to stick with the product rule because, I mean, that's the name of the PowerPoint. So we should probably get some practice in that. F prime of y. Notice the fact that it's of y doesn't really make a difference. It's my v times u prime plus u times v prime. Ideally, you should be distributing this in and simplifying it. I'm just a little crunched on time. All right, so then we get this guy. This guy is our first problem where you could not hide from the product rule if you don't like the product rule. This square root is going to block me from distributing in the way I worked with other things. At this point, it should probably be noted. I usually wait for a student to discover this, but seeing as how I'm not there, that's probably going to be hard for me to notice. So I'm going to refer to this as Nora's rule, because that's my daughter. So Nora's rule says that if y equals the square root of x plus or minus a, then y prime is always going to be 1 over 2 square root of x plus or minus a. This is a pretty awesome rule to have, because without Nora's rule, we would have to take the limit as h approaches 0 for this kind of little side problem and figure out what its derivative is. It's 100% possible, but it's just a lot more writing rather than just knowing Nora's rule. So if my u is 3x and my v is the square root of x minus 5, u prime is simply 3, and v prime, according to Nora's rule, is, whoops, I already messed that up, 1 over 2 square root of x minus 5. So when I put together my dy dx, which is what my problem's asking for, I can take v times u prime, which is outside the parentheses, plus u times v prime. And you're perfectly welcome to use Nora's rule. It's not official calculus the way product rule is, but you're welcome to use Nora's rule as a shortcut for these square root problems. Note, if the x has got a coefficient or if the x has an exponent, if it's at all more complicated, it doesn't work. You really need fancier tricks to pull that off. But if it's just x or plus or minus a number, you can use Nora's rule. All right, so for this guy, we're looking for dy dx. dy dx means we should start off by getting y by itself. So I'll add the 15 over, subtract the 4x, divide by the negative 3. And now I've got it as y equals. Once I have it as y equals, I can find my dy dx just by taking my derivative like normal. It just looks a little different. And I get dy dx equals 4/3. Which kind of makes sense because this is a classic line. So it makes sense that a classic line would have a classic slope as opposed to an equation. All right, this one's a little funky with this f of x in there. My u is 3x to the 4th, and my v is f of x. Again, I don't have a choice here. I really have to use product rule. My u prime is just going to be 12x cubed. My v prime at first seems like, how on earth could I possibly know that? But it's actually really, really easy. The derivative of f is f prime. So my dy dx is going to be u times v prime, which is f prime, plus u prime times v. And I'm all set up. This is a fantastic test problem because if you know what you're doing, it's very straightforward. And if you don't know what you're doing, I find out really quick. Hint, hint. All right, so this problem, we got ourselves a parabola, and we want our tangent line to be parallel to this line. So probably a good idea just to remind ourselves that the slope of this line is 3. For our parabola, if we want to know the slope of the tangent line to the parabola, that means we want a derivative. Just to show that we've got choices, I want to multiply that x in. I'm going to say my y prime is 2x plus 1. So this is my derivative. Remember, the derivative is kind of like a generator of the slope of the tangent. If I want a tangent with a slope of 3, I set my generator equal to 3. If I solve this, I find out that x is 1. So the coordinate that's going to have a tangent with a slope of 3, thereby being parallel to this line, is going to be the coordinate with an x value of 1. If I really want a y value to be able to end this problem, I need to take this 1 and go back to the original equation to get a y value. 1 squared plus 1 is going to be 2. So the coordinate that has all those characteristics is 1, 2. I don't think we have enough time to do this problem because it's a beast. Basically, the idea here is that you've got a parabola looking something like that, and you've got this point. There's 2 lines that are going to be tangent to the parabola through this point. Maybe one there, and maybe one way up high. The idea here is that you want to try and create this scenario. So I know that the slope is going to be 2x plus 1. And I know the x value is 2 and the y value is negative 3. So I could try and set up my equation of a line, y plus 3 equals the slope, which is not a number, it's an equation, and then x minus 2. The only problem is I've got too many variables. The big find in this problem is that y equals this stuff. So I can replace the y with that quadratic, and then I have a fancy equation. I could solve this, FOIL this together, get everybody on the same side, either factor a quadratic formula of the quadratic that results, and then I get the two x values of these 2 points. Once I know the x values, they ask for the slope. I take those two x values and I plug them back in my slope equation, 2x plus 1, to find out the slopes of those two lines. I'm short on time, so I can't really go through that, but at least now you have a plan as to how you might approach that. I challenge you to try and finish it on your own. This is a great problem. This is taken off an AP test. Again, it's a good problem for if you know what you're doing, it's not at all hard. But if you don't know what you're doing, it's pretty intimidating. The secret is to start off with y equals uv. We're looking for y prime of 2, which means I need to find y prime. Luckily, this is pretty much the exact definition of when to use a product rule. I've got a u times v. So I could say u prime v plus uv prime. If I'm looking for y prime at 2, kind of function notation, that means I'm looking for u prime at 2 times v at 2 plus u at 2 times v prime at 2. Now, this is function notation. This is not multiplication. Well, u prime at 2, I know is negative 4. And v at 2, I know up top is 1. U of 2, they tell me, is 3. V prime of 2, they tell me, is 2. Negative 4 plus 6 is going to be 2. And I've got an answer. So really, if they offer you all of this data, ignore it for a moment, figure out what the problem looks like, and then figure out how you can use that data to get a numeric answer. All right, our last problem is taking a look at what could be pretty simple. The derivative of x is just 1. Roots. A good idea here is to rewrite the problem as 2/5. Remember, this is the numerator and this is the denominator. So this 2/5 is going to come out front. And then it's a fraction, so you got to be a little careful. I want to take 2/5 minus 1. 2/5 minus 1 is going to be negative 3/5. And there we go. We get a little sample of how to work with the product rule. Enjoy.